Welcome everyone to this video on our discussion of statistical thermodynamics. In this video, we're just mainly going to first review some just general concepts, ideas of statistics. Okay, so right, let's just first consider the idea of probability. Okay, likelihood of an outcome, probability of something happening, right? So the probability that one specific outcome happens over all other possible outcomes, okay, is related with, just the number of times that one specific outcome can happen divided by the number of times any other outcome can happen, right? Or all possible outcomes, including the one you're interested in, can happen, right? So that's right? Pi over Ni divided by N total is just saying, right? Ni is the total number of desired outcomes, right? Right. Well, N total is the number of possible outcomes, right? And so the probability that the one you want to have happens, right, is just related with that, okay? Right, and so let's consider, for example, flipping a coin 4 times, right? And what's the probability of getting heads twice, right? So if I flip a coin 4 times, right, we can consider all of the different possible combinations of results from flipping a coin 4 different times, okay? Right, now, if I want to consider the total number of ways I can get heads twice, right, I have 6 different ways, right? Heads, TT, HT, right, HTTH, so on and so forth, right? So there's 6 different ways where heads appears twice, okay? Right, with flipping a coin 4 times, right? And I'm not going to write out all the different ways of results that you can get for flipping a coin, right? But, right, the total number of results you can get by flipping a coin n times, right, is really the fact that, right, for flipping a coin once, right, for one flip, right, we have 2 results, right? For the second flip, we have 2 other results. For the third flip, we have 2 other results, so on and so forth, right? Well, right, the different outcomes that I can get is just then a product of those things, right? So for one flip, it's just 2 different results, right? For 2 flips, the total number of results would be 2 to the 2 power, and so on and so forth. So in general, okay, the total number of flips is just 2 to the n power. In this case, n is 4, so 16 total things, right? Total possibilities, right? And in terms of getting 6 different ways you can get heads twice, that you can get from this combinatorial kind of method here of 4 choose 2. I have 4 outcomes and I want 2 specific results. I want 2 heads out of those 4 outcomes. And so that formula for that is 4 factorial over 2 factorial times 2 factorial. It's the total number of outcomes divided by the number of outcomes you want, factorial times the total number minus the number of outcomes you want, factorial. Okay. Right. And so there's 6 different ways that this can occur. Right. And again, there's 2 to the 4 or 16 total ways I can get different outcomes, right? Because each flip is independent of the previous one, right? So the probability of getting heads twice is 6 divided by 16, which is 38%, right? So 38% of the time you flip a coin 4 times, you will get heads twice. That's it, right? Okay. Let's consider 10 flips, right? And think about what is the probability of getting heads 5 times, right? So I'm still considering half of my flips are heads, right? And the other half are tails, right? In whatever order they appear, doesn't matter, but that's what I want, right? So if I flip a coin 10 times, I want half heads, half tails, right? So the total number of ways I can get 5 heads out of 10 coin flips is 252. Okay. And then the total different outcomes I can get is 2 to the 10 power, which ends up being 1024. Okay. And so the probability of getting half, for 10 coin flips, getting 5 heads and 5 tails, that probability is 25%, right? So 25% of the time I flip a coin 10 times, I'm going to get 5 heads, right? The other 75%, I'm going to get something different, okay? So notice that getting half heads and the other half tails out of some even number of coin flips, right, is decreasing as the total number of coin flips increases, right? And so this percentage of getting one specific outcome, say half heads, half tails, right, is decreasing as the total number of chances, right, events that can happen, right? And that percentage will trend towards 0 as your total number of flips goes to infinity. Okay, right, and that probability of getting half of the heads is related with this function here. Okay, that won't really you should talk much about, but if you ever wanted to calculate it from some whatever number of coin flips, right, there it is. Okay. And if you look at the limit of that as n goes to infinity, that thing goes to 0. Okay. And so yeah, right. But again, so again, the likelihood that I get half heads, half tails, that likelihood, that probability goes to 0 as the number of coin flips increases, right? But if I still ask you, right, without talking about that, right, if I still ask you and I just said, hey, what is the most likely outcome if I flip a coin 1,000 times, right? And you would tell me, well, the most likely, most probable, the most realistic outcome to occur is if you have 500 heads and 500 tails, right? I would say, yeah, half heads, half tails is the most likely outcome, okay? And that is true, okay? So there's a big difference between the probability of a specific outcome and which outcome is more likely, right? So just because the probability of a specific outcome goes towards 0 as the number of possible outcomes goes to infinity, doesn't mean that that outcome isn't the most probable, isn't the most likely, right? It's just as you have more and more and more events occurring, right? Right. It's more likely that you have some random event that occurs, right? And not your most likely outcome, right? So you're kind of distributing the possibilities over a wider and wider range of possible outcomes, and so that decreases the likelihood of any specific outcome, okay? But that doesn't change which outcome, say, is the most probable, okay, the most likely to occur, right? And this is very much tied in and related with statistical thermodynamics, because statistical thermodynamics basically, you can derive all of thermodynamics using statistics and your quantum mechanical energy levels and such. That one can get through quantum chemistry, right? And so basically you have, through quantum mechanics, a set of energy levels and such that one can obtain, right? And then I can ask what's the likelihood of my molecules having this type of energy, right? What's the probability of my molecules being in this energy level, this energy state, having this translational energy, having this rotational energy, and so on and so forth, right? And then I can relate that probability and that likelihood of that occurring to then essentially talking about the average energies of your system, right? So all of thermodynamics, all the things we've been talking about in thermodynamics, right, is really talking about kind of the average energy, the average entropy, the average Gibbs free energy, right, our system, of our set of molecules, right? If I have an Avogadro number of molecules, right, a mole of molecules, right, there's a lot of molecules in there, right? And so it's not that every molecule has the exact same energy, same entropy, same Gibbs energy. There's a distribution, right? But we can get a lot of information on talking about the average value, right? And so yeah, right, and so that's what kind of statistical thermodynamics is all about. Okay, and so again, it's this link, this behavior between the microscopic to macroscopic, and it's going to be related around Boltzmann statistics and this partition function Q that we'll talk about in other videos.